Hello everyone. Today we are going to present a study about novel solar powered desalination system. This study was conducted at the United Arab Emirates University, and this research was supported by the university's National Water and Energy Center, where their work focuses on sustainable water solutions using renewable energy technologies. Here is the outline of today's presentation. We will start with an introduction to the topic and its importance. Then we will describe the desalination process used in the study, followed by the main equations that govern this performance. After that, we will walk you through the experimental setup and how the system was tested. We will also look at how the researchers handled uncertainty in their measurements, and then we will share the results and discussion, highlighting the key findings. And finally, we will end with the conclusions and implications of the study. Now, let's look at the main objectives of this study. The first one is that the researchers aim to introduce an innovative approach to HDH desalination systems by using the direct solar energy along with a low energy ultrasonic atomizer. Second, they want to evaluate the thermal performance of the system when exposed to direct sunlight to see how well it works in real conditions. And third, the goal was to investigate how ultrasonic automation affects the efficiency of the system, especially in terms of evaporation, humidification, and freshwater production. In short, the study is all about making solar desalination systems more effective, efficiency, and more sustainable. So, let's begin with a bit of introduction. Freshwater scarcity is a serious global issue, especially in arid regions. One sustainable solution is using solar powered HDH desalination systems, which work by evaporating and condensing seawater to produce fresh water. While HDH systems are already useful, they can be made more efficient by improving their design. This study presents a new system that combines direct solar energy with low energy ultrasonic atomizer, which creates fine mist droplets that evaporate more easily. Even though ultrasonic automation has been used in other desalination setups, its use with direct solar HDH systems hasn't been fully explored. So this research aims to fill that gap and improve freshwater production using clean and renewable energy. Solar air water heating. To improve HDH system performance using solar energy, engineers often use solar collectors and concentrators to heat both the air and the water. Research shows that solar radiation directly affects how productive the system is. More sunlight means more fresh water. Higher ambient temperatures also help. However, there's a challenge. We need to get the most output from a small solar collector area while keeping energy use low. Waste heat and heat pump cycle. Another way to improve HDH system is by using waste heat or integrating heat pumps. These hybrid systems have been shown to produce more fresh water and use energy more efficiently. But there's a limit. If the temperature, especially in the dehumidifier, gets too high, the system performance can reduce. Packing material. The materials used inside the humidifier can make a big difference. Packing materials with a high surface area to volume ratio, small size, and low packing density allow for better evaporation. Materials like cellulose and honeycomb paper have worked especially well and help to improve the gained output ratio. Mass extraction. Controlling the flow of air and moisture between the humidifier and the humidifier can help improve energy efficiency. Studies show that using a single extraction point instead of none or multiple balances the system better and significantly increases the GOR absorption cycle. By adding this step, using materials like silica gel or calcium chloride, systems can recover heat and improve freshwater output. Also, using subsurface or indirect cooling techniques boost the performance, but the effectiveness depends a lot on airflow and how heat is transferred. Ultrasonic atomization. Finally, recent studies have looked at ultrasonic atomizers, which create fine mist droplets that evaporate more easily, and these have mainly been used in solar steels, not HDH systems with direct solar input. However, when applied correctly, they can improve both evaporation and fresh water production, especially if combined with spray system.
Let me explain the desalination process of the system as illustrated in Figure 1. The system consists of four main components: the humidifier, which also acts as a solar collector, the dehumidifier, the seawater tank, and the freshwater tank. At the top of the system, we have the humidifier, where solar radiation is captured through a transparent glass cover. The solar energy heats the seawater inside the humidifier. An ultrasonic atomizer placed near the inlet transforms seawater into micro droplets, which are suspended in the air. These fine droplets have a higher surface area and evaporate more efficiently under direct solar radiation. As warm air moves from the inlet to the outlet, it carries the water vapor with it. This enables the evaporation process thanks to both natural convection and ultrasonic atomization. The moist air then enters the humidifier section where 20 spray nozzles, arranged in the fishbone pattern, cool the air. These nozzles spray fresh water from the freshwater tank, causing the water vapor in the air to condense and collect as fresh water. The system operates in a closed loop. Seawater is supplied periodically from the seawater tank into the humidifier. The freshwater tank collects the condensed water from the humidifier and recirculates it back through the spray nozzles. This design allows for efficient thermal desalination using direct solar energy with minimal extra power, making it highly suitable for remote or off-grid regions. Now I will explain the basic equations that govern the performance of the system. In the humidifier, the process starts when seawater is atomized into very fine droplets at the inlet. These droplets are carried by air and are assumed to fully evaporate by the time they reach the outlet. The top of the humidifier is transparent, which allows direct solar radiation to enter. This radiation helps heat the water, and the heat causes the droplets to evaporate more efficiently. The system follows an energy balance, which is shown in equation 1. It says that to the local energy entering the humidifier equals the energy leaving it, plus the heat loss to the surroundings. In equation 2, you can see how the energy entering the humidifier is calculated. This includes the energy carried by the incoming air and the seawater. Equation 3 shows the energy leaving the humidifier, which comes from the heated air and the vapor. Then, in equation 4, the energy losses are calculated. This depends on the temperature difference between the humidifier and the ambient air, and how well the system is insulated. To evaluate how effective the system is, two performance indicators are used. The first one is called year or error, or gained output ratio. As shown in equation 5, it tells us how much fresh water is produced for each unit of thermal energy input. The second one is RR, or recovery ratio. In equation 6, this ratio tells us what portion of the seawater is converted into freshwater. These equations help us understand to the energy flow in the system and how efficient the desalination process is. This desalination system includes seven main components. The humidifier, also called the solar receiver, where seawater is exposed to solar radiation. The dehumidifier of condenser, where vapor turns back into liquid. The seawater tank, which stores the saline water used in the process. The freshwater tank, where clean water is collected after condensation. The ultrasonic atomizer, placed at the humidifier inlet, which creates tiny droplets for better evaporation. The spray arrangement used in the dehumidifier to enhance condensation, and tank insulation to reduce heat loss and improve efficiency. In this system, the humidifier has a transparent glass cover that allows direct sunlight to heat the water. Inside, two small fans maintain the airflow at a speed of 1 meter per second. Freshwater is pumped from the freshwater tank into sprayed nozzles of the dehumidifier. These nozzles help the water vapor to condense by direct contact, and the condensed water is returned to the tank in a closed loop. The seawater tank has a capacity of 80 liters and supplies water periodically to keep the humidifier filled. The same goes from the freshwater tank, which also holds 80 liters and is equipped with a cooling coil. This coil helps maintain a low temperature by removing heat collected during condensation. As the process continues, the water level drops in the humidifier due to evaporation, so it is refilled regularly from the seawater tank to keep the atomizer working properly. Let's now look at Figure 3, which shows the ambient temperature on two topical days during the experiment. As we can see, the temperature rises quickly around 10:30 to 11 a.m. and stays high until about 14:30. On both days, the temperature range between 30 to 40 degrees Celsius, which is ideal for solar desalination. This date helps explain how the performance of the system changes during the day. When the solar flux is high, between 8,000 and 1,000 watts per square meter, the seawater heats is up more, which leads to more evaporation and higher freshwater production. These initial water temperatures were around 28 plus or minus 2 degrees Celsius in the humidifier and 25 plus or minus 2 degrees Celsius in the freshwater tank. At the end of the day, freshwater temperatures rose to about 36 degrees Celsius or more, especially when solar radiation was strong.
Uncertainty measurement. And this section focuses on the accuracy of the experimental results, especially the performance indicators of the HDH systems, the gain output radio, and the recovery radio. To calculate how precise the results are, the researchers used a method called the root sum square. This method helps account for how small errors in the measurements, like temperature, humidity, solar radiation, and water flow, can affect the final results. All these uncertainties are combined mathematically to estimate the total error in GOR and RR. This kind of analysis is essential because it tells us how reliable and trustworthy the performance data really is.
Well, I'm going to continue with the results and discussion. In this investigation, since the temperature of the sweater inside the humidifier is capturing direct solar energy, the temperature increases inside the humidifier. This temperature is recorded as the ultrasonic atomizer temperature operating continuously. For the experiment, peak and ambient temperature variations were observed in the range of 32 and 45 degrees Celsius. Full day temperature variations at the inlet and outlet of the humidifier are shown in the picture number 4. The temperature of the outlet of humidifier is linearly increasing until the time is 14 o'clock. Then it decreases as time passes. This indicates that the solar energy input the humidifier is having a similar pattern increasing the saline water temperature. The temperature profile observed at the inlet of the humidifier increases linearly, then decreases in the afternoon and decay gradually. The temperature observation of 40 days is shown in picture number 5, indicating temperatures at the inlet and the outlet of humidifier. For the first 4 days, the difference is significantly higher as compared to other days, and then it decreases gradually until day 7. The lower difference is observed for day 11 and day 14. The maximum temperature observed at the outline is 66.65 degrees, and the maximum temperature observed at the inlet is 43.9 degrees. A similar observation was predicted. The peak outlet temperature reached near to 50 degrees. The humidifier inlet and outlet temperatures indicate had similar temperature profiles with peak temperature occurring at the time 13 o'clock. The peak is also observed, and this peak was closer to 13 o'clock. This delay of 60 minutes in the peak was compared with the peak of solar radiation at 12 o'clock. The delay was attributed to the heating capacity of the water. These results indicate that the temperature range of the inlet temperature of humidifier were between 35 and 70 degrees, and maximum temperature of 63 degrees at air mass flow rate of 0.014. The temperature range of the outlet temperatures of humidifier were between 35 and 65 degrees, and maximum temperature of 58 degrees, at air mass flow rate of 0.014. At the, lead, at the least mass flow rate of air was 0.0086 kilograms per second. The results found the humidifier outlet temperature approximately 60 degrees and found the outlet temperature from the solar collector higher above 60 degrees, and this can be attributed to the higher temperature input dehumidifier. The variations in the relative humidify measurements at the inlet and outlet of humidifier are shown in the figure number 6. As shown in figure number 6, the relative humidity in the lowest as the peak time closer to the time 13. The inlet relative humidify at the beginning is higher and then it decreases gradually at the inlet of the humidifier. This indicates that the increasing rate of dehumidification at the air vapor mixture exits from the dehumidifier enters to humidifier. The rate of condensation increases and as the vapor content in the air increases with time through capturing solar energy, reaching its peak value during the midday.
Freshwater productivity in HDH systems, humidification and dehumidification system can be significantly improved by integrating ultrasonic atomizers and carefully managing several key operating parameters. The recovery ratio, which is the proportion of freshwater produced to seawater supplied, reached a maximum value of 64% at around 2:30 p.m. Interestingly, this peak occurred about an hour and a half after the maximum solar radiation was recorded at 1 p.m., showing a delay due to the high heat capacity of water, which takes time to absorb, store, and transfer energy. Similarly, the GOR-Hein output ratio followed a stable upward trend, reflecting consistent collection of freshwater. It is influenced by the amount of energy entering the system, and in this case, it closely followed the pattern of solar input. In this study, only a single ultrasonic atomizer was used, but earlier research shows that increasing the number of atomizers from 2 to 6, for example, can improve the DHR by nearly 10%. However, this increase is not unlimited. Excessive automation can reduce the transparency of the humidifier chamber, making it harder for sunlight to penetrate. This reduces internal temperature and leads to uneven heat distribution, which negatively affects the evaporation rate and overall efficiency. Besides atomization, other factors have a strong impact on productivity, increasing the air mass flow rate and its temperature changes the relative humidity at the outlet of the humidifier, promoting better evaporation and higher freshwater output. Likewise, increasing the saline water flow rate and temperature also contributes to greater productivity. For instance, at 20 degrees Celsius, increasing water temperature can lead to a full unit rise in GOR, but there's a limit to much heat can reduce the effectiveness of the dehumidifier. Salinity is another critical variable. As salinity increases, but productivity and GOR tend to decrease. When salinity goes beyond 13 grams
fertilizer, the system requires more input energy to achieve the design of both due to lower vapor pressure and reduced water molecular activity. System pressure is also important. Reducing the pressure in the humidifier improves humidification, increasing water production by up to 50%. On the other hand, increasing pressure in the dehumidifier can enhance condensation and raise productivity by more than 200%. Lastly, the physical size of the system plays a role. Increasing the length of the dehumidifier decreases GOR but might increase water output. In contrast, the humidifier length shows a positive effect up to a certain point, after which performance drops again. In conclusion, using ultrasonic atomizers in HDH systems exposed to direct solar radiation can significantly improve freshwater productivity. However, for best results, a careful balance must be maintained between atomization, solar energy input, air and water flow rates, temperature, pressure, and system design. Too much of any one factor can reduce efficiency. So, optimization is key to achieving stable and efficient operation of the system. This study investigated the integration of an ultrasonic atomizer device within a direct solar energy powered HDH desalination system, focusing on its thermal performance and freshwater productivity. The results demonstrated that ultrasonic atomization significantly changes the humidifier's performance, increases the evaporation rate, and improves overall desalination efficiency due to variations in ambient conditions, particularly solar flux, freshwater production, fluctuated throughout the study period. The system achieved a maximum daily productivity of 8.92 liters per day, while the average daily production yield was 4.6 liters per day when operation for 6 hours with a 1.54 square meter solar collector area. The key contribution of this research lies in leveraging the direct solar energy absorption by atomized water droplets within the humidifier, introducing a novel humidification approach not previously explored in the literature. This system has significant potential for small-scale off-grid desalination applications, particularly in remote coastal regions and communities where conventional desalination is impractical due to energy constraints. However, certain limitations must be addressed for practical implementation. These include periodic humidifier maintenance to sustain optimal evaporation efficiency, careful control of atomizer density to prevent excessive mist formation that reduce solar penetration, and seasonal variation in productivity due to fluctuations in solar radiation levels. For future research, the system efficiency and stability can be enhanced by optimizing atomizer placement, refining operating parameters, and developing a responsive model to adapt to daily solar variations. Additionally, integrating thermal energy storage could enable continuous operation by utilizing stored thermal energy during periods of lower absent solar radiation, theory, improving system reliability, and extending operational hours.